record. All right, so last week's chapter talked about adaptations to resistance training. And now we're going to talk about adaptations to the other kind of training, which is aerobic, or using oxygen, or running on a treadmill for a long period of time, or doing battle ropes or high intensity interval training. So aerobic training is training that is involving your body's ability to take in oxygen and utilize that oxygen for glycolysis. And anaerobic training would be more exercises that are associated with the bioenergetic systems of phosphagen or your fast glycolysis. So there's either you're doing resistance training or aerobic training. And when you're doing resistance training, the changes are going to happen predominantly to the neuromuscular system. So your neurons and your muscles. When you're doing endurance training, the adaptations are going to be more so that in the neuromuscular system, so that you have more protein, that you get stronger. Your muscles, there's increased muscle size, and increased muscle size equals increased strength. And then increased strength equals increased power and increased muscle size. So the changes to the body that are going to happen because of resistance training are all to increase muscle size. But with aerobic and aerobic training, what we're trying to do is we're trying to utilize ATP more effectively. And in the aerobic training portion specifically of this, what we're trying to do is we're trying to do more work and use less oxygen. All right, oxygen is our indicator of work efficiency. If the activity needs more oxygen, it's not as efficient. All right, so we want to do aerobic training so that our ability to utilize oxygen and create ATP is enhanced. So some of the adaptations are going to be related to your blood vessels. So there's going to be an increased number of capillaries, the little teeniest blood vessels that are going to innervate your muscle fibers. So there's going to be an increase in capillaries. There's going to be an increase in the ability for your heart to capillaries. It's going to be an increase in the functioning of your heart. All right, and particularly the stroke volume of your heart is going to increase, and your heart rate is going to decrease. All right, so the heart is going to do less work, which is indicated by a reduced heart rate, and it's going to pump more blood, which is an indicator of increased stroke volume. And heart rate and stroke volume, when you multiply those together, those are referred to as cardiac output. So your heart will begin to put out more doing less because it's able to take in more blood. So this refers to stroke volume. The volume of blood for every beat or every stroke of the heart will increase. And that means that if the heart is stronger and pumping more blood, it doesn't have to beat as many times per minute. All right, so typically the adaptations to aerobic and anaerobic training are going to have to do with the distribution of oxygen and ATP throughout the bloodstream. The chapter is organized as such. In the beginning, it will discuss adaptations to aerobic training. When we do our typical run on the treadmill for 35, 45 minutes, 3 days a week, that is one way of working aerobics, or one way of working your bioenergetic systems associated with, endurance training. But there's other ways. And so my athletes, I want to work their bioenergetics. I want to work their body's ability to take in oxygen potentially and utilize ATP. But I'm not going to do typical endurance training of running on a treadmill. I'm going to do things like battle rope training in order to my anaerobic training. So if I want to work at the aerobic level, I have to, again, apply that concept of specificity of training. If I have individuals who are running half marathons, then they should be working and training their aerobic capacity. And if they work their aerobic capacity, this will improve. For my athletes, though, my athletes, gymnasts, are only doing things for 70 seconds or less. And 70 seconds is the longest routine. In fact, they get deducted for doing a floor routine that lasts longer than 70 seconds. So for me to have my athletes do aerobic training, classic aerobic training, might not actually target the appropriate bioenergetic system. Now, during the off season, I would have my athletes do aerobic training, but that's only so that they can get improvements in anaerobic training. For instance, if they do aerobic training, they're going to increase their ability or their heart response. So their heart is going to get stronger. And if their heart is stronger, when it comes time to bring oxygen during anaerobic training, the heart will be better equipped to do it. All right, there's also going to be, say, for instance, because of aerobic training, there's going to be an increase in lung function. And that means that the lungs are going to expand, the intercostal muscles will get stronger, and then the heart and the lung will be able to function better. And if the heart and lungs function better, when I do, for instance, burn all of their ATP doing battle ropes, then because their heart and lungs function better, they'll be able to get back enough ATP faster so that they can do another bout of anaerobic training. So with my athletes during the off season, if they want to do running and I'm like, 1.5, 2, 3 mile runs, those are fine with me. But I only do the aerobic training for my gymnasts so that I can improve heart and lung function so that they can get better at doing anaerobic training. So for my gymnasts, I'm going to do things aerobic training during the off season, and then start to transition to more anaerobic training during the regular season because it's more appropriate to what they're doing. All right, so the chapter will talk about adaptations to both of these. But again, most of the adaptations in this chapter are going to be to promote increased heart and increased lung function and increased ability to distribute oxygen and ATP throughout the system so that you can get fuel and you can burn sugars. Okay. Cardiorespiratory endurance. Cardio is heart and respiratory is lungs and the ability to get blood and oxygen everywhere in your body. All right. So as you do exercise, aerobic training, your cardio, your heart will change and your lungs and blood vessels will change. And these changes are all going to be to promote oxygen diffusion throughout tissues and to bring energy and ATP to your muscle fibers, all right, in the bloodstream. So the easier the blood can get through the blood vessels to the tissues, the better it can distribute ATP and oxygen to the muscle fibers. So with improvements in cardiorespiratory endurance, there's going to be heart and blood vessel improvements, lung improvements, and then there's going to be changes at the muscle and metabolic level as well. So the muscle will adapt. All right, type 1 muscle fibers will grow and hypertrophy and get bigger and stronger. And your ability to break down ATP because of enzymatic activity can also improve. All right, so with endurance training, there's going to be an increase in the amount of oxygen I can pull into my body. And VO2 max is the main indicator of increased maximal endurance capacity. So we're going to have to get assessments of VO2 max. Now, how do you measure VO2 max? Well, you can do that with direct measurement of the air that's inspired and exhaled with a machine, or what we could do is we could try to estimate this VO2 max. And because we don't have complex machinery in the lab, what I'm going to do is try to teach you, whoopsies, I'm going to try to teach you the Queen's College Step Test. Super easy. All you need is a step. All right, it's going to be about 16 centimeters. Sorry, not 16 centimeters. Let's go 16 inches. It's 22 centimeters. It's actually bigger than that, but doesn't matter. You need to have a step, and then you go up and down the step for 3 minutes. And at the end of the 3 minutes, what you're going to do is you're going to measure not VO2 max, but you're going to measure heart rate. All right, you're going to measure heart rate, because heart rate and VO2 max are correlated with each other. And I'll show you a couple of equations. They're directly proportional. All right, and when they're directly proportional, that means if the heart rate goes up, then the VO2 max goes up, or the VO2 max, the heart rate would go up to respond to the body's need to get more oxygen. Remember, the heart is going to be pumping blood, and blood has hemoglobin and oxygen. So in order to get the oxygen to the body more effectively, the heart rate goes up. So heart rate is an estimate, or can be used as an estimate of VO2 max. So all of these endurance training assessments, the 1.5-mile walk test, the Queen's College Step Test, the Strand Rhyming Test, the YMCA bike test, they're all based on the fact that heart rate and VO2 max are correlated. An individual who has higher endurance training is going to have a lower heart rate at the same submax exercise intensity. Submax means that for normal individuals, their maximum heart rate should be about 220 minus your age. All right, so if I'm 44 years old, max heart rate is equal to 220, 220, and let's just average my age to 40. So minus 40. So that's about 180. So when I'm doing exercise, if my heart rate gets to about 180 beats per minute, that's indicating that I'm doing a maximum effort, a maximum cardiac effort, and therefore that would not be submaximal exercise intensity. If I do exercise and I get my heart rate to 180, I'm doing a maximum effort. But for an individual who has higher endurance training than myself, if we are doing a submaximal effort, like a 3-minute kind of slower effort, 3-minute of going up and down a stair, that should be submaximal. For an individual who's trained, they're going to have a lower heart rate than I'm going to have. All right, and that's because their heart is pumping more effectively. They're able to pull more oxygen in. Their heart is stronger. It's able to force more blood out of it during systolic blood pressure, or the systole phase of the heart contraction. And because of that, they can get more oxygen to the system easier than I can. So with training, so you can see pre-training is in blue, and you can see post-training is in red. And you can see that the overall value of VO2 max for those individuals who've trained goes much higher. So typical values of VO2 max for an untrained individual will be about, 45, or average values, 45 milliliters per kilogram per minute. So that's milliliters of oxygen per kilogram per minute. So milliliters per kilogram per minute. I am about, I'd say 60 kilograms. So I'm 60 kilograms. And then at 60 kilograms in 1 minute, 60 kilograms. And milliliters is about 35 milliliters, 45 milliliters. So 45 milliliters. And that 45 milliliters is also the same as, I believe, 0.45 liters. All right. And then times 1 for 1 minute. All right. 1 minute. So that's going to give you an assessment of how many milliliters a 60 kilogram person would need. And this is how many liters, rather, how many liters a 60 kilogram person would need. And it's about, say, 2 point, I think 5 or 3. It's actually, sorry, not 2.5. It's about 3 or so, 3.5 liters or 3 liters a minute. All right. Okay, so not only can a trained individual get to a higher overall VO2 max, but they can also go further into a bout of activity and continue into a more intense activity. So an individual who is not trained is going to top off at about 12 kilometers per hour, at least this individual. But the person who's trained, not only are they going to have a lower VO2 max, or sorry, a relatively similar VO2 max at that particular intensity, but they're able to get a higher intensity or go further into the bout of activity and allow that VO2 max to improve more. So not only are they going to have a higher absolute value of VO2 max, but they're going to get that VO2 max at a more intense activity or bout of activity. So most of the cardiovascular changes are going to come from these particular variables. And what's going to happen is your heart size is going to increase with training, particularly the strength and the size of the walls of the ventricles. There's going to be an increase in stroke volume. There's going to be a reduction in heart rate. There's going to be an increase in overall cardiac output. There's going to be an increase in the volume of blood flow. There's going to be an increase in systolic blood pressure, but there's going to be a decrease in diastolic blood pressure. And then there's going to be an increase in overall blood volume potentially. So these are all changes that are going to happen at the heart level, cardio. All right. And then the vascular changes are going to have to do with increased capillary, increased difference between the oxygen concentration and the carbon dioxide concentration in the alveoli and in the cellular level. So there's a better diffusion of oxygen and carbon dioxide. Sorry. All right, so let's get into these changes here. So this Fick equation here, it relates VO2, so you can see VO2, or the rate of exchange of oxygen in the system. All right, this rate of I guess utilization of the volume of oxygen that's in the system has to do with the stroke volume times heart rate times the atrial ventricular difference in oxygen. So the ability for the body to utilize oxygen has to do with the amount of blood that the heart can pull in, multiplied by the number of times the heart is beating per minute, multiplied by the difference between the concentration of oxygen in the blood versus the concentration of oxygen at the alveoli level. An increase in VO2 max is correlated here. See, it's like, it's not start value divided by heart rate. Its heart rate is directly proportional to VO2 max. So usually if you graph something like VO2 max and you graph heart rate, as one increases, the other increases. So they're like a linear relationship. So we can use this value of heart rate, maximum heart rate, as an indirect indicator of VO2 max, which is why we can use the Queen's College step test and the heart rate response to submaximal exercise as our indicator of VO2. When training occurs, heart mass is going to increase. All right, this is the left ventricle. The left ventricle volume increases. And I mean, this isn't exactly or at all what a heart looks like, but we all know this drawing, so I may as well just go like this. Cut the heart in half. And then this is looking at the heart, like if the person is here, their heart is here, and they're looking this way, and they're looking at me like this. This is the heart, all right? So this would be their right side. So this is their right, and I remember ventricle, like this, and this is the right atrium. And then this is the left ventricle, the left atrium. And this is where the blood is coming in through the vena cava here. Blood comes in. Blood goes through a valve. Blood goes through the valve. Blood leaves here and goes to the lungs. Then blood comes in from the lungs into here. And then blood leaves here through the aorta. There's another valve here. So with exercise training, heart mass and the left ventricular volume increase. Actually, let me think. I think I have this actually opposite, but I think it's actually like this. This is the left atrium. Atrium is up. Hold on one second. Why am I going to brain fart on this right now? Let's just take a look. I want to make sure I'm not labeling things wrong. That's in the beginning of chapter 6. Yeah. I knew I was wrong. Left atrium, aorta, pulmonary valve, right atrium. Atrium is up, ventricle is down. Correct. So let's go like this. Erase this. Erase that. Erase this. Erase this. Erase this. All right, so this is actually correct. This is your right, oh boy. This is your right atrium. Atrium. Ventricle. Ventricle, that's right. So the left ventricle here is the one right before the blood goes to the aorta. That's the one that's going to be actually contracting to squeeze the blood out of the aorta back into the body. And even though I was kind of like bonking, the way that I usually remember this is atrium is pointed upward, the A is pointed upward, and the ventricle, the V, is pointed downward. So the atria is at the top and the ventricle is at the bottom. So it comes from the vena cava into the right atria, through the valve, out of the right ventricle into the lungs. There's no oxygen in this blood. Then the blood gets oxygenated from the lungs, comes back into the left atria, out of the valve, into the left ventricle, and boom, into the aorta. And at this stage of the game, the oxygen is, or the blood is oxygenated and can go to the body. So with training, there's an increase in overall heart mass. This is a muscle, right? The heart is a muscle. And when a muscle increases its training, then the muscle is going to get stronger and it's going to get bigger, just like any other muscle would. And when the muscle gets bigger, it's going to be able to, like, stronger, or size, muscle size is correlated with muscle strength. So when the size of the heart increases, the heart will be able to contract harder. Then because it can contract harder, it's going to increase. And not only that, but the cell walls of the left ventricle get thicker. So it'll be able to squeeze harder. And if it can squeeze harder, then it can push more blood out for every heartbeat. So as the target pulse rate increases, as the pulse of the exercise that I'm doing, or as the exercise increases its intensity, the pulse rate, or the amount that my heart will have to beat, increases. So as the pulse rate of my activity increases, there's going to be a greater emphasis or stress on the muscles of my heart, which will make it so that my heart hypertrophies. And when it hypertrophies, it's going to push more blood out and increase the stroke volume. Not only that, but the blood plasma volume. Imagine if the blood volume was actually, like, very low. Like if you had like a little pool in, like, the Sahara. All right. At first, there would be plenty of water for all of the sediment in the pool. But eventually, as the volume of water in that little, like in that hippopotamus pool, as the volume of water decreased, all of a sudden the water would start to become murky and it would become mucky. And then if the volume of water was really low, all you'd be left with is this very thick mud pool. All right. And then you see, like, the nature shows, all the catfish are flopping around in this big mud pool. All right. It's because the volume of water in that particular pool evaporated and it's left over with all the rest of the kind of sediment. And that makes it so that the plasma becomes very viscous or thick. So with training, what happens is there's an increase in plasma volume. There's an increase in the liquidity, or there's a decrease in the thickness of the blood plasma. And because of that, it's going to, the blood, or the blood plasma, will be able to get into the very teeniest of capillaries. So there's an increase in blood plasma volume, which is going to make it so that there's more blood leaving and more fluid leaving the left ventricle. And that means that there's an increase in the end diastolic volume. All right. There's an increase in the ability to get blood into the heart. And that's going to increase the overall amount of blood that can get squirted out of the heart. All right. So this increased plasma volume allows for the heart to be able to do more work and get more oxygen to the teeniest of blood vessels without necessarily increasing heart size or the strength of the heart at all. It's just distributing more oxygen because the blood gets a little bit potentially thinner. So this is looking at, like, the left ventricle diameter and a couple of other size related. This is left ventricle mass. And you can see that with endurance exercises, particularly running and cycling, you'll see that, oopsies, particularly with running and cycling, you'll see that there's a greater increase in left ventricle mass and other key physiological changes to the actual cell, to the actual tissue strength and size of the heart itself. There will be increases in these variables for strength athletes, but notably much higher increases in the integrity of the heart tissue itself with endurance training. So the cardiac output, or the ability for the heart to distribute oxygen and blood, is related to heart rate times stroke volume. And we've already kind of talked a little bit about heart rate. For an individual who is not trained, their heart rate will be higher than an individual who is trained. So with exercise, what happens is this is going to be reversed. All right, the heart rate is going to reduce, but the cardiac output has to increase to distribute more oxygen and fuel to the system. So your only other option to increase your cardiac output is to increase stroke volume. So how does that happen? Well, stroke volume is the amount of blood that can actually get squirted out of the heart when the heart contracts. So if there's more blood, that's going to help. So what happens is the plasma volume increases. There's more liquid, there's more plasma fluid. And if there's more plasma fluid, then what happens is that's going to increase the amount of, of, of blood that can actually get sucked into the heart. All right, so let's just resting in some maximum heart rate decreases with training. All right, so with training, the resting and submax heart rate decreases, but that means that there's going to be an increase in stroke volume. One of those is, imagine if I'm doing a submax exercise, I'm at 80%, my heart is beating pretty fast. Ba-boom, 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 ba-boom. If my heart is pounding, I just don't have enough time for my heart to relax enough so that it can fill. Right? If my heart is beating, boom, 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 that only leaves like a second for my heart to relax enough to suck enough blood in. Well, if I can reduce the number of times per minute my heart is beating, then that gives more time while my heart is relaxing during my diastole, my heart's relaxing phase. It gives more time for my heart to suck in blood. And if that's the case, it increases the filling time. So my heart rate decreases, and what that does is it allows for more blood to be pulled into the heart. And we're going to talk about what happens to blood pressure too, but I may as well just do it right now. While you're exercising, you have your systolic blood pressure, but then you also have your diastolic blood pressure. So what happens to both of those? Well, while I'm exercising, as the demand for exercise, and let's even go like this. Let's maybe make a graph. And this is time. And we could also say intensity probably. As the time increases, or the intensity of the exercise increases, my systolic blood pressure is going to also increase. I don't necessarily know what steepness this graph is, right? It's not relevant, like relative to any other steepness. So I'm just going to go like this: systolic blood pressure. And my systolic blood pressure with time will increase. And this is in millimeters of mercury. All right, that's how it would be measured with your sphygmomanometer, in the millimeters of mercury. All right, but my diastolic blood pressure is going to be very different. My diastolic blood pressure, especially if I'm a trained athlete, might stay the same, and it might actually, let's even change that, undo, just a different color so it's easy to see. My diastolic blood pressure might actually stay the same or drop a little bit. So when your heart is beating in systole, all right, what happens is your heart is beating, and your heart is going to squeeze really tight, and it's going to squeeze, and it's going to contract, and that's going to increase the pressure inside of the heart. And remember, things usually go from a high pressure to a low pressure. All right, so you have a high pressure situation, increased pressure, usually things are going to drop down to low pressures. So when the heart is relaxed and it's not contracting at all, let's just do two different hearts. Let's do another heart here. This is during systolic blood pressure. This is going normal. And then this is going to be diastolic blood pressure. All right, so what the heart looks like for both of them. All right, now, normally, let's just say my heart is at rest. I mean, my heart is still beating, but let's say it's in between a contraction. It's not contracting, nor is it squeezing. It's going to have, say, a blood pressure of 120 divided by diastole. Let's say it's going to be 100. All right, let's say just 100. 100 units of mercury. All right, millimeters of mercury, 100. All right. Now, when my heart is in systole, it's squeezing really tight. So the pressure inside the heart is going to increase, which means the pressure in the heart is very high compared to the pressure outside of the heart. And things go usually from a high pressure to a low pressure. Things go from a high to a low. So during systole, when my heart beats and it squeezes, there's a very high increase in pressure, and that's going to promote blood flow. I'll even go like this. That's going to promote blood flow out of the heart. All right, because obviously when you squeeze something, you increase pressure. And when you increase pressure, all right, it's going to squirt everything out. That's what's happening when you squeeze something. Or if I take a bag of icing and I squeeze the bag, you increase the pressure. What happens is the icing comes out the bottom of the hole. So by your heart contracting, it increases the pressure inside of the heart, and the blood leaves the heart because of that change in pressure, the pressure gradient. All right. Now, same thing. So when I exercise, I want to get more blood out of the heart, out of the heart, out of the heart. So naturally, what's going to happen is as my bout of activity increases, as I keep going further and further into time, and especially if the intensity of the exercise increases, my heart is going to beat harder and harder and harder and harder and harder. And if with every beat, my systolic blood pressure increases, that's pretty much like saying with every beat, my heart is going to squeeze harder and harder, and it's going to squeeze every little drop of blood that it can out of the heart eventually. All right, so there's going to be a more forceful, increased force of contraction with training. There's going to be more blood in the left ventricle, and that heart is going to increase its force of contraction. It's going to be a higher pressure inside the heart because of this increased force of contraction, and it's going to promote more of blood flow out of the heart. So your systolic blood pressure will increase. All right, then what happens to the diastolic blood pressure? Well, with my diastolic blood pressure, what's going to happen is my heart is going to be relaxing here. And the more my heart relaxes, the less my heart contracts, the more it just relaxes. All right, what's going to happen is there's going to be now a negative pressure inside the heart. It's almost like a vacuum. And with training, what you want to do is you want to increase this filling time, but you want to increase right here this diastolic volume. You want to increase the end diastolic volume. So in diastole, your heart is relaxing. And when it's relaxed, it's creating a very low pressure, like a vacuum in the heart. And because of that, it's going to promote blood flow back into the right atrium so that you can get blood into the heart, back into the lungs, and eventually out through your systolic blood pressure or your systolic contraction. Well, that means that what we actually want here is for the heart to relax even more. And if the heart can relax, if the tension in the musculature of the heart can be reduced even more, then there'll be a greater pressure drop in the heart, which is going to promote more of this sucking of the blood in from the vena cava. So for a well-trained athlete, actually, this diastolic blood pressure is actually going to drop more than for a normally trained athlete. That's going to like absolutely kill all of the tension in the musculature of the heart, make the heart relax more, make it so that there's less pressure. And if there's less pressure, it creates a better vacuum. And if it creates a better vacuum, it can increase the amount of blood that's coming into the left ventricle and that's coming into the right atrium, and increase the amount of blood that I can get in during diastole, which is going to help increase my stroke volume, especially if my heart is strong enough at the end of this relaxation phase to be able to squirt out all the rest of the blood. So with training, your systolic blood pressure can increase because of the increased force of contraction, but the diastolic blood pressure can stay the same. And for really well-trained individuals, the diastolic blood pressure can actually drop 5 or 10% to make sure that you can increase the amount of end diastolic volume. Anybody have any questions? So this is showing stroke volume, the amount of blood that I can get out with each beat, the milliliters of blood that I can expel from the heart with each beat. So for an individual who is not trained, their stroke volume is going to be somewhat lower, always lower than the trained individual. And they're going to have to get off the treadmill at an earlier time because they just cannot distribute enough oxygen to the body. They're going to get into their blood lactate level. They're not going to be able to continue to utilize oxygen as effectively to create ATP, and they're going to have to get off the treadmill sooner. So individuals who are trained not only have a higher VO2 max, and can go into a longer bout of exercise because of a higher VO2 max, but now also because of the ability to get blood out of the heart, their stroke volume will increase. So those are two major adaptations to exercise training. So in regards to cardiovascular changes, there's going to be an overall reduction in heart rate. All right, and now that can be pretty dramatic. So if I can do my, and this is one of the labs that you just had for heart rate, or that you guys are working on right now. If I can do a little bit of exercise, I can reduce my resting heart rate, and I can reduce my resting heart rate about 1 minute, a beat per minute. And there are a number of minutes per week. So, I mean, there's 60 minutes in an hour, 3,600, blah, blah, blah. If you do the math, you can save your heart a number of beats. And that's what your lab is looking at. Now, why is it important to save your heartbeat? Well, if the heart is a muscle, eventually that muscle is going to get tired. So if we can save our heart from beating, that's going to make it so that we can use our heart longer. So what you're going to do is you're going to figure out what your resting heart rate is, and then what would happen to your resting heart rate if you were to reduce it by 4 beats per minute or 6 beats per minute. How many heartbeats would you save over the course of your lifetime? Now, this resting heart rate is going to reduce. And remember, the parasympathetic, the P part, has this downward part. So a reduction in heart rate is going to be accompanied by or correlated with an increase in parasympathetic activity and a reduction in sympathetic activity. All right, so remember, your body increases heart rate, blood pressure, all of that stuff when it thinks it should run or fight, and that's your sympathetic nervous system. Your parasympathetic nervous system is rest and digest. So with aerobic training, the body doesn't think that this bout of activity is intense enough to increase the resting heart rate. All right, so it's an adaptation that your not only the musculature of your heart rate, but now all of a sudden your autonomic nervous system is also beginning to become affected. And what it means is that for somebody who is trained, their submaximal heart rate is going to go down for the same absolute intensity of exercise. So I can use an estimate of VO2 max. I can use heart rate and measure heart rate, which is why your 1.5 mile walk test, your YMCA bike test, your Bruce treadmill protocol, your Queen's College step test, all of these assessments of VO2 max are all based on your heart rate's response to various bouts of activity. So with the submaximal heart rate, what will happen is, let's say you have time here, and not only do you have time increasing here, but there's also intensity of the exercise increases. And let's say, for instance, let's say you have time 5, 10 minutes, 15 minutes, 20 minutes, 25 minutes, 30 minutes. And at each one of these things, there's going to be an increased intensity. Well, what the heart rate will do is, let's say this is heart rate. All right, this is heart rate over here. Well, I'm going to erase this for a second. And let's just do this, erase. And let's go like this. Just make it a little bit closer to here. Let's go like this and put heart rate here. So as the time increases, and as the intensity increases from 5 minutes to 10 minutes, your heart rate will look kind of like it'll start at a particular value, it'll increase and plateau. And then it'll increase to the next bout of activity, and then it'll plateau. And then it'll increase because of the next increase in intensity, and then it'll plateau. And then it'll increase with the next intensity, and then it'll plateau. And then it'll increase with the next bout of exercise at a different intensity. So your heart rate will plateau. All right, this is your heart rate's response to varying or increased intensity of exercise. All right, so if I exercise, I increase the intensity, my blood needs more, my heart and my body needs more blood. Your heart rate will increase until it has the right amount of blood, and then the heart rate's not going to keep climbing. It'll steady state. Your heart will reach steady state because of a given intensity. Now, I increase the intensity again. I take the dial. I increase the tension on the bike. Oh my God, my body's like, oh man, I need to get more blood. What am I going to do? Okay, well, I'll increase heart rate. I'll increase heart rate until I get enough blood, and then my heart will kind of like steady out. It will plateau, and it will be beating faster, but it doesn't have to go faster and faster. And then I increase the intensity again, and then my heart rate is going to increase so I can get more blood flow. Now, this is the basis of a graded exercise test. A graded exercise test, like the Bruce treadmill protocol. You'll be on the treadmill will be at 2 miles per hour with a particular incline. My heart rate will increase, it'll plateau. Then the next 5 minutes, I increase the speed again. And then what I do is increase the incline, and then I'll see the heart rate response again. And I can measure these heart rate responses to varying intensities and a graded increase in exercise intensity. And I can measure this heart rate response, and that is an indicator of my VO2 max and how my VO2 max or my oxygen consumption would behave, because heart rate and VO2 are linearly correlated. All right, now my sub-maximal heart rate for somebody who is trained is going to look less than this. All right, I can't, this is just like a model, but it'll have a lower heart rate, a lower heart rate, a lower heart rate for every given intensity for somebody who's trained. All right, because their heart rate doesn't have to beat as hard because their stroke volume is going to increase. for an individual there who's training, their maximum heart rate is always going to be this 220 minus your age, 220 minus age. And the statistics or the research suggests that this is not really impacted a huge amount by training. So as you get older, as you get more fit, this 220 minus your age in regards to your maximum heart rate is still going to hold true. But submaximal heart rates are going to be impacted positively in the sense that your submaximal heart rate will decrease or be more effective if you're more trained. That's why if your heart rate response at the end of your Queen's College step test is higher than mine, then I'm more fit than you. So we're going to use the Queen's College step test in our lab as an indicator of VO2 max. All right, so in a week or so, I'm going to have you guys do the Queen's College step test. All right, so anybody have any questions? All right. So your cardiovascular changes are going to happen because of interactions with heart rate and stroke volume. It's not all of the changes happen because of heart rate. Not all of the changes happen because of stroke volume. More so, it's probably the interaction between the two that's going to make it so that your heart can pump out the blood that it needs to in order to provide the body with the oxygen and fuel it needs for those particular bouts of aerobic training. Not only does your heart have to beat less because your heart is stronger and it can deliver more blood per volume, but your heart rate will also recover faster with training. All right, and so remember your cardiac output is equal to heart rate times stroke volume. So although the heart rate is reducing, because the stroke volume is increasing at a relatively higher in a higher capacity than heart rate, the cardiac output doesn't suffer because of this reduction in heart rate. It goes up because of this increase in stroke volume. Okay. So the next graph here shows a little bit of what a typical heart rate response would be like for a particular bout of exercise. So this exercise intensity is at a particular value. I'm not sure what the intensity of this bout of exercise is, but at 0 time, before the exercise even starts, the intensity is going to be very, very low. And because of that, the heart rate doesn't really have to adjust. So this is like about 60 beats per minute, 60 beats per minute. And this is for somebody who is pre-trained, the blue. So we'll say that this person has a heart rate of, I don't know, like let's say 85 beats per minute, not tachycardic, but 85 beats per minute. Then they're going to exercise. When they're resting, all right, that's before exercise happens. Then regardless of the intensity of the exercise, even if it's just a small walk, the exercise itself is going to require an increase in oxygen. All right, increase in oxygen. So as soon as I start to exercise, my heartbeat is going to start to increase. Now notice it gets to about a steady state at about, say for instance, about 2 minutes of exercise. One of the things that we want to consider is how long do we do a good warm-up, and what is this warm-up doing? All right, so a warm-up is trying to accomplish a couple things. Number one, it's trying to increase body temp. All right, and it's going to increase body temperature by bringing blood, which is 98.6 degrees, to the body. All right, right now you have a lot of blood in your belly when you're sitting. When you exercise, you need to get that blood out of your intestines and stomach and into the muscles so you can increase the muscle temperature. And if you increase muscle temperature, you're going to make it so that your muscles are less stiff. All right, lower the K of the muscles. Just like if I put Play-Doh into the microwave, the Play-Doh becomes less stiff. So I want to increase muscle temperature by getting blood flow. I also want to increase my heart rate, right? Increase heart rate, because if I can get my heart to go a little bit higher, then I can distribute blood to my body. I also want to increase my lung capacity, my breathing rate. Let's just say my tidal volume. All right, if I can breathe more, then I can get more oxygen. Number 4, what I want to do is I want to have a release of adrenaline. And from my adrenal glands, adrenaline. And remember, adrenaline is a catecholamine also called, what is it? Let's put Drew on the spot. What is it, Drew? Tell us. You can do it, Drew.
What was the question?
Adrenaline
Oh,
is a catecholamine that's released by the adrenal cortex. That's also called what? What is adrenaline called? They give it to you in a EpiPen.
epinephrine.
Hey, Drew did it. So this is called epinephrine. And Drew, is epinephrine and norepinephrine, is that working with your parasympathetic or sympathetic nervous system? Epinephrine. Does epinephrine make your heart and heart rate go up, or does it make it go down?
Oh,
Right, so it's going to be a sympathetic nervous system. All right, Drew, boom. So it's going to, a warm up is also going to make it so that your adrenaline, which is a hormone, can be released from your adrenal glands and cause your sympathetic nervous system to kind of engage and increase your heart rate. So really this a warm up is designed to do these things so that you can have increased oxygen capacity to the muscles. All right. So how long does a warm up last? Well, this says here, well, in order for my heart to even reach steady state, given that bout of activity, I need to go at least 2 to 3 minutes. All right. So your warm up needs to at least be 3 minutes long. That's just to start to impact your heart rate, or for the heart rate response to stabilize. So I start to exercise, my body needs more and more blood. All right, now if I exercise very, very intensely, this heart rate response is going to be even higher. But let's say this is just a submaximal bout of activity. All right, like I'm standing on the treadmill doing nothing. And then right here at time 0, I turn on the treadmill to 2.5 miles per hour. Not a lot, not very much. It's just a slow walk. Well, my body is going to need more oxygen, so my heart is going to beat. It's going to increase its number of beats per minute. Maybe it's going to go from, now this seems to be 200, right? 200 beats per minute. Remember, if my heart rate goes from 220 minus my age, which is about 40, and my heart rate gets to about 180 beats per minute, 180, then that bout of activity is really, really intense for me. It's a maximum bout of activity. When I look over here, man, this is pretty close to about 200. So I know that just looking at this value here, I know that this is a very intense exercise. It's getting this pre-trained person's heart rate almost up to 200. So, and it's way past 150. This is almost up to like 195. So I know that this person who's doing this bout of activity is not 40 years old. Otherwise, they would have reached their maximum capacity. And probably this exercise trainer or the person doing the assessment would probably have stopped the assessment prior to when it got to this point, if they were 40 years old. So this person is 220 minus their age. Let's say 220 minus 20 years old. Minus 20 means that they don't want their heart rate, their max heart rate, to go below 200 beats per minute, and you notice that they're not quite at 200 beats per minute. So I would assume that the person that they're working with in this particular assessment was a young adult under the age of 20. They didn't get to their VO2, their heart rate maximum, so they allowed this assessment to go. So this is a very, very high intensity exercise that they're doing for 4 minutes. And you'll notice that for this individual, for both individuals, or for this individual post and pre-training, their heart rate went up. And then after about a minute, 2 minutes, maybe 2 minutes of activity, their body was getting enough oxygen. The VO2 max needed was reached. So the heart rate could plateau. The heart rate doesn't have to keep increasing until it explodes. The heart was able to match the oxygen needed for that bout of activity. So the heart rate response plateaus. And then what you can do is you can measure where the heart rate plateaued. So this is minute 1, minute 2, sorry, this is minute 2, minute 3, minute 4, minute 5, minute 6. And the way that this Queen's College step test works is what you're going to do is you're going to do a bout of 3 minutes of activity. And what's really interesting is if you look at, even though, you know, Cassie is a girl and Tatiana's curly hair and Drew's a guy and he plays hockey, we have all of these differences. One really interesting thing is this response is very, very similar for everybody. Very similar no matter who you are. So what the Queen's College step test does is it gives you a metronome. So you have to walk up and down this little step at a defined intensity. So the intensity for everybody is the same. The intensity is based on a metronome. All right, so the intensity is the same. The stair height is the same. And because of that, that's going to cause everybody's heart rate to increase to a particular amount, but it's going to be less than their 220 minus their age. The heart rate increases, and for normal individuals, it's going to plateau. Now, for an individual who is trained, post-training, theirs is going to plateau much lower than mine. I'm not trained. And what you're going to do is you're going to measure the heart rate. Measure the heart rate at minute 1, it's still increasing. Measure the heart rate at minute 2, it's still increasing. Measure the heart rate at minute 3. That's why the Queen's College step test lasts 3 minutes. It gives enough time for the heart rate to start to plateau at a submax exercise rate. Then what you're going to do is have your client take a heart rate. All right, that heart rate is going to be, say, for instance, the heart rate at minute 2 is, I don't know, let's say the heart rate is 170. And then at minute 3, the heart rate is 178. And then at minute 4, the heart rate is 179. And then at minute 5, the heart rate is 179. Well, then you know that they have reached this. You have 3 heart rates here that are within 1 beat of each other. Then you know that this individual's heart rate has plateaued. And you're going to average these plateaued heart rates, probably going to get something to about 179. And then that number can be plugged into some normative charts, and you can get an assessment of their VO2 max. So you're going to have somebody do a Queen's College step test. You're going to take their heart rate. At the end of this 3 minutes, you're going to take their heart rate, measure their heart rate, take the measured heart rate that at the end of the 3 minutes, it's assumed, especially at a submax work rate, it's assumed that their heart rate response has plateaued. You're going to take that plateaued heart rate, plug it into a particular graph, and that will give you an assessment of their VO2 max. Way easier than doing a direct capture of gas breathed in and gas breathed out. Now, is it going to be as accurate? Is the standard error of the estimate of using your heart rate to estimate VO2 max? Will the standard error of that estimating procedure be higher than if we just actually captured your VO2 max? Yeah, sure. But when they compare the heart rate method of estimating VO2 max with the regular VO2 max using the Queen's College step test, it's statistically correlated. So we can use heart rate as an indicator of VO2 max because of this response, this predicted response that we can get with heart rate to sub-maximal exercise workloads. And we already know that an individual who's trained will have slightly lower heart rate values than individuals who are not trained. Now we can use heart rate and this response in our lab as our main method for measuring VO2 max, even if we don't have all of these direct capture mechanisms. So this is a pretty important graph, especially for our lab and for the resources that we have. Does anybody have any questions about that? Cool. So you'll notice again in liters per minute, absolute liters per minute, cardiac output, which again is heart rate times stroke volume, heart rate times stroke volume. That cardiac output is going to increase with training. So not only is it the heart rate that's increasing and plateauing, but it's the cardiac output that's increasing and plateauing. And you'll notice that the cardiac output plateaus, but not as dramatically as your heart rate. So that means that although the heart rate is plateauing, the cardiac output is still increasing because of changes at this stage in stroke volume. So once the heart rate plateaus, all right, at about 2 minutes or so, any further increases in that bout of or that increased cardiac output has got to be due to my stroke volume. So there are other, aside from the heart actually changing its muscle wall size and strength or being able to pull more blood into it, there are other parts of the cardio, not just the heart, but the vascular system that is going to potentially adapt. Number one is going to be an increase in blood flow. Now, how does the blood flow more effectively? Well, a couple of different ways. Number one, it's going to increase capillarization. So at the muscle fiber, there's going to be increased capillaries. And capillaries are the very, very teeniest little blood vessels. So with training, maybe a blood vessel will come down and look like this. But then with training, let's say it looks like this. Blood vessel looks like this. Well, with training, what'll happen is the little capillaries, the little vein, the little teeniest of veins will continue to grow, and you'll get offshoots of capillaries from the veins so that blood can innervate the muscle fibers even more. And now these little teeny venules and capillaries are so thin that if the blood was really thick, it would just not be thin enough to get into these little teeny vesicles and veins and blood vessels and capillaries. So what happens is the blood flow starts to become, or the blood becomes very thin, or because there's an increase in blood volume, or there's an increase in the fluidity of the blood, there's a reduction in the thickness. And if there's a reduction in the thickness or the viscosity of the blood, and the blood is thinner, then the blood is going to be able to get into the very ends of these venules more effectively. All right. And then if that's the case, then these capillaries can fill up with blood more effectively and get to these muscle fibers and bring more oxygen and more blood flow to the active muscle. So there's going to be an increased capillarization. There's also right now, when you're sitting and you're resting, you have all of this food, and all of the food is in your belly, and the food is digesting and moving around and going through your intestines and this and that. and that takes blood. And in order for your 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 macronutrients to dissolve and then get absorbed into the bloodstream, you need to get blood into the small intestines. Well, that blood in the small intestines is going to reduce blood flow to the muscles. So what happens is, as I exercise, the blood flow to my stomach and my intestines is redirected to my active regions. All right, that's going to increase blood flow to the active muscle because there's less blood flow happening in my gastrointestinal tract. So there's going to be an increase in capillarization, right? Some of the capillaries, they might not necessarily grow extra, but with no exercise or no training, just blood might not be getting to these very teeniest blood vessels. So there's going to be increased capillarization. More capillaries are going to grow. More capillaries are going to be used. There's going to be a reduction in blood flow to the regions that aren't being utilized in terms of that activity. And then there's going to be an increase in total blood volume, which reduces the thickness, and it allows for the heart to get blood to the teeniest of blood vessels. We talked about systolic and increased blood pressure with exercise and a reduction in diastolic blood volume, blood pressure. And that's so that during systole, the heart is squeezing really, really hard and increasing the pressure inside the heart. And that's going to force more blood out of the heart. And if it forces more blood outside of the heart, it's going to increase the pressure at which the blood is pushing or coursing through the arteries. There is going to be a reduction in diastolic blood pressure. And if there's a reduction in pressure, even more so than the heart is at a lower pressure than the vena cava, then that's going to allow for more blood to get sucked into the heart as the heart is relaxing. So the heart relaxes even more. It creates an even greater vacuum, and that pulls more blood into the heart so that during the systolic contraction, there's more blood in the heart to squeeze out. All right. And we just talked about the blood volume increasing. Now, the hematocrit, the percentage of blood or hemoglobin within the blood will drop potentially. So even though your blood plasma volume is going to increase, the number of cells in the blood that's going to attach to oxygen may decrease in regards to its percentages, but I'll show you why. That's because for an individual who is untrained, all right, this is an untrained individual, they're going to have a particular amount of red blood cells, say 2.2 liters of red blood cells in their blood, but their plasma volume is 2.8 liters. So 2.8, 2.2, divide those, you have a hematocrit level of 44%. But notice they have less red blood cells. This person, after training, has more red blood cells, but their blood plasma volume is even higher. It's taken and retained water from the kidneys so that the total blood plasma volume is higher. Notice right now, this individual has 5 liters of blood. This individual has 5.7 liters of blood. So 7 liters of fluid have been retained by the kidneys. Remember, we talked about the ADH, and all of the kidneys are an extra endocrine gland when you're exercising in high heat. And so the blood plasma volume is going to increase, although the percentage of hematocrit decreases. It's actually more red blood cells, but divided by a higher blood volume. So the hematocrit value decreases with training, but that's only because there's higher amount of fluid. There's actually a higher concentration of red blood cells, and a better ability to attach to oxygen and deliver those oxygen molecules to the muscle fibers. But because this blood is thinner, all right, because the blood has less viscosity to it, that blood can actually get to those very teeniest of capillaries and blood vessels when it's coursing through the system. All right, and now now we're pretty much finished our discussion about the heart and the veins, the vesicles, all right, the vascular system. And now what we want to do is talk about respiration and talk about what happens to the lungs with aerobic training. All right, well, one of the very cool things is that humans walk very differently than animals. So when a human walks, let's go like this. When an animal that has 4 legs walks, let's do this. Let's do this. Let's try to draw a picture here. And this is a horse. And then this is going to be their front leg. And then this is going to be their big belly. This is going to be their other leg. This is going to be the tail. And I have another foot in the back here. All right, so one cool thing about human beings is that we walk on 2 feet. And this is going to be a great adaptation for us, all right? So I have this horse here. Does anybody ever watch a horse race before? Anybody ever watch a horse race? All right, Cassie, you ever watch a horse race before?
Yeah, I've seen one before.
You ever see a marathon horse race? How long are the horse races that you typically will see?
I mean, I've just seen like a brief. I haven't watched like a full one. I've just seen it happen quickly.
How long do they last for? They last for a couple hours or they last for a couple minutes?
A couple minutes.
So Cassie notices that the horse races that she's seen have been brief. You ever see a horse run a marathon? You ever see a horse race last for 26 miles?
No.
You ever think about that? How come they have human races that last for 26 miles, but they have horse races that don't last for 26 miles? You ever think about that? Why are horse races brief? In fact, you'll see like the Kentucky Derby, they run 1.5 miles, 1.5 miles. Whereas a marathon is 26 miles, 26.2 miles. What is up with this? Well, it has to do with how your lungs work, how your lungs respond to aerobics. Now, when a horse runs, a horse is running obviously on 4 legs. When a human runs, a human is only running on 2 feet. In fact, in Sweden, every year they have a horse versus human marathon where they have people start a marathon, they run, and 10 minutes later or sometime later, they have people on horses and they chase the people who have started the marathon. And sometimes the people who are running the marathon, they win in a time that's greater than 10 minutes more than when the horse is left, which means that the human being is running the marathon faster than the horse. Now, does anybody find that unbelievable? Does anybody find it unbelievable that a human can beat a horse in a marathon? And does anybody maybe have an idea of why that would happen? Why would it be the case that a human can beat a horse in a marathon. It used to be the case that North American Indians, they even have this kind of like historically represented in poems and things and stuff. They would have a way of hunting deer where they would be able to track the deer through the woods, and they would be able to run after the deer, catch up to the deer, and they would be able to like grab the deer by the horns and break the deer's neck. They wouldn't even need to hit with any arrow or spear or anything like that. They'd just be able to run up on the deer and break the deer's neck. Does anybody have a dog? Anybody here have a dog? Yeah, Sydney, you have a dog?
Yeah, she's right here.
Oh, what's the dog's name?
Callie.
Let's see. Aw, cute.
She thinks we're playing right now. So
Aw. All right, so Sydney, when you walk the dog, do you ever walk the dog in the woods off leash?
I'm gonna be honest, she's like a cat. She'll just lay down at the bottom of the driveway and stop walking.
Okay, so does she walk ever on her own? Does she like to walk on her own ever?
Yeah, in the house. She's not very adventurous.
Okay, I mean, in all fairness, she doesn't look like a dog that needs a huge amount of activity or whatever.
Yeah.
Does maybe this isn't necessarily the most perfect example. Does anybody have a bigger dog? Does anybody have a dog that needs a little bit of running time? Cassie, what kind of dog do you have?
I have a black lab mix.
Okay, so do you ever take your dog into the woods and let it run off leash while you're walking?
Yes.
What does the dog do?
He just roams around, but doesn't go too far away.
So let's say you're walking through the woods. Does the dog run up ahead of you?
A little bit, but he doesn't like run away.
Right, but it will run up ahead, and then what it is, it runs up ahead, and then what does it do?
He'll come back and then like just explore.
So it runs up ahead, and then it'll stop up there and turn around and pant and wait for you to kind of like catch up to it, and then it'll run off again, and then it'll stop and pant and wait for you to catch up to it again. You ever experienced that?
Yes.
All right, and what have you ever gone on a jog with the dog on leash and just run with the dog?
Yes.
And what does the dog seem to enjoy more? Being off leash and doing what it wants, or following you the whole time?
Off leash.
Okay. Why would that be the case? And why would it be the case that I've never met Cassie, nor have I spent any time with her dog, obviously, but I'm able to predict certain behaviors? Well, a dog's and a horse and any quadrupedal animal for that matter has a very different way of walking than we do. And because of that, it has a very different way of its lungs being able to function than we do. Human beings are very good at endurance exercise, aerobic exercise, and it has to do with how we're, like, I guess, organized or situated in terms of our physiology and in our anatomy. So when a horse hits its front feet on the ground, all right, a horse hits its front legs on the ground, the legs are going to hit down into the ground, but because of Newton's laws, the ground is going to push back up on the legs. And when the ground pushes back up onto the legs, it forces the musculature and the skeleton of these legs, the skeletal structure and the bones, it forces the legs to push up in this direction. Not only do the legs push down into the ground, but the ground pushes up into the legs. And it forces, every time the front legs of a horse hit the ground, it forces the horse to expire. So a horse is limited to a 1-to-1 breath to step ratio. A dog is limited to a 1-to-1 breath to step ratio. Anything that walks on 4 feet is limited to a 1-to-1 breath to step ratio. Every time the horse takes a step and hits its front legs, it forces it to breathe out. All right, every time a human being hits their feet on the ground, the vertebrae and all of the musculature firing eccentrically can dissipate that force. So it doesn't force a human being to take a breath every time it hits its feet. So when you're walking a couple of steps, you can take one breath for every, say, for instance, 8 steps or even more. And when you run, what happens? Let's say I run, and instead of taking one breath for every 8 steps, okay, Cassie, what happens when I run? How many breaths will I take then for every 8 steps when I run?
More than one?
I could breathe much more than that. I could take 3 breaths for every 8 steps. I can change how my breath and how my breathing rate functions per step that I take. My pulmonary ventilation can change. And because of that, I can use more oxygen for every bout of activity if I need to. But a horse cannot do that. Your dog cannot do that. Your dog is limited to a 1-to-1 breath to step ratio. So after about 5 minutes of my warm up, all right, my heart rate goes up, my breathing rate goes up, and my breath to step ratio is going to increase. But a horse cannot. A horse is limited to 1-to-1. So what happens is a horse is going to run pretty much as fast as it can, and then it becomes exhausted, tired. It can't get in any more oxygen. It reaches its lactate threshold. The horse needs to rest. The temperature, the internal temperature of the horse increases. The horse needs to stop and pant and rest. Then, when the horse gets rest, it can run again for another 1.5 miles or whatever until it needs rest again. Your dog is going to run up ahead of you. It's going to have fun running, but eventually, because it only has a 1-to-1 breath to step ratio, its pulmonary ventilation and its limitation to this 1-to-1 breath to step ratio is going to make it so that it cannot continue to run. It needs to stop and rest. We can run much further because we can alter our breath to step ratio. If you look at a map, say, of Massachusetts, let's go like this. Whoopsies. Maybe this will screw everything up, but let's go like this. If you look at a map of Massachusetts, and this is typically Massachusetts, not some of the states that are in the western part of the country, because of when the colonies were founded. But if you look at a map of Massachusetts, it might look like this. Right? That's kind of maybe what it looks like. And if you look at the towns, you would think that if you're going to make a town, what you would do is you would take the state, you would cut it like this. All right, you would separate it like that, and you might make like a couple of lines this way, and you might make it so that this is what the towns are. This is one town, this is another town, this is another town, but that's not what the towns in Massachusetts look like. What they look like is something like this, right? Let's change the color. They look like something like this. And they're all kind of like uneven in terms of what their land area looks like. All right. But if I say, for instance, look at this here, 1 second. Maybe we may as well finish. If I look at where their town centers are, the town centers are like this, all evenly distributed. They're all the same distance away from each other. So even though the actual towns have these weird outlines, right? If I look at the distribution of, if I look at the distribution of the town centers, the town centers are all relatively evenly distributed with each other. I want to erase that. And I want to erase this and this and this and this and this and this. Sorry, I'm just erasing too many of these the dots. But if you erase all the lines that indicate where the towns are, and you look at the town centers of the towns in Massachusetts, you'll know that notice that they're all relatively evenly spaced in terms of distance away from each other. Now, where did the town centers in Massachusetts, how did they become established? Was it random placement of town centers? Or why would it look like that the town centers are evenly distributed in terms of their distance, but the actual town lines that designate the town are very random? Why would that happen? Does anybody have any ideas? Does anybody kind of know what I'm talking about? So if you look at the towns, right, they might look like this. They might be very weird shaped in Massachusetts, right? But if you get rid of the town borders or the borders of each of the towns, all of their land, all of their centers of the town are all evenly distributed. Does anybody know why that would be?
Did it have something to do with the farmland or just the land in general and following, at least around Mendon? My grandpa told me that it was like following the rivers. The rivers kind of outlined the farmland, and then town borders were created kind of around that.
Okay, so let's say these town borders are dictated. I have no idea who that was because I don't have you up here, and I can't. Who was that? That was, who am I talking to?
Tatiana.
Oh, Tatiana. So I would agree. I think that a lot of these borders here were probably because of rivers and water, right? As Tatiana says, but the placement of the town centers within those borders is not based on the location of rivers and stuff like that. The town locations are more evenly distributed. And that's because what would happen is a horse would run from this town center to that town center and need rest. And in order for the horse to rest, they would make a place for the person who's riding the horse to also rest and get a drink of water and to rest their feet and their back and sit down and get a beer. And this is where the town centers started to develop from. So a horse would run as far as it could and then have to stop, and then they'd make a saloon. And then the horse would run as far as it could and have to stop, and then make another saloon. And then the town centers started to establish around where the horse could run and how far a horse could run. But because a horse is limited to a 1-to-1 breath to step ratio, that horse could only run a particular distance until it would have to stop. And then that's how the town centers got established in an equidistant fashion in Massachusetts. All right, although the borders of the town were not evenly distributed because, as Tatiana says, it could have to do with water supply and things like that. The town centers and the saloons are more evenly distributed because that's how far a horse could run with its limited breath to step ratio before it needs a rest. All right, 1 second. Let's get rid of this. So one interesting thing about human beings is that we are able to change our pulmonary ventilation. we are able to change our breath to step ratio given particular bouts of activity. And some of the changes in VO2 max, or the ability to get oxygen to my body, are a result of changed ventilation rates. All right, now that's comparing human beings that are bipedal to quadrupedal animals, and it makes us very, very efficient walkers. It's one of the things that defines human beings from other mammals, is that we don't walk on 4 feet. And what that does is, it not only does it free your hands up to be able to not only does it free your hands up to be able to manipulate tools and manipulate things in the environment and become systems with other things, but it also makes it so that your legs don't impact your cardiorespiratory system when you're running and walking, and that makes us even better utilizers of oxygen. So with training, your respiratory rate is becomes better. All right, I can have less breathing at any given bout of activity because my lungs get bigger. All right, my intercostal muscles get stronger, my diaphragm gets bigger, and that all sucks more air into my lungs, increases my tidal volume. And if I can get more air and more oxygen in, then my pulmonary ventilation can go down. I can breathe less times per second. Now, Drew is pretty fit, I would bet. If he skates for 2.5 minutes, he's barely going to get out of breath. If I skate for 2.5 minutes, my heart rate is going to have to go through the roof. My lungs are going to have to breathe much faster. My ventilation rate, my frequency, my respiratory frequency is going to increase. Frequency is always something per minute, right? So Drew is going to breathe, say, I don't know, 100 times per minute. I'm going to breathe 300 times per minute because I'm not trained, and my respiratory ventilation is going to be much higher. It needs to be higher, probably because Drew's heart is stronger, it is bigger, he's much younger, and his lungs are probably bigger than mine. All right. So my pulmonary ventilation is going to be much less effective than Drew. Pulmonary diffusion is, there's a diffusion of oxygen, oxygenated blood with non-oxygenated blood. And that diffusion, all right, across the alveoli into my blood vessels, the diffusion is going to be, or the difference in pressure of oxygen in my blood compared to oxygen in the air that I breathe in is going to be different. So there's going to be better pulmonary diffusion. And let's say the opposite of training. Let's say I smoke cigarettes or lots of weed or whatever, and my alveoli are destroyed, then I just don't have tissue that's thin enough for oxygen to diffuse. And because of that, I'm not going to be able to get enough oxygen to my muscles. So for an individual who is trained, the opposite will occur. The diffusion of oxygen through the alveolar tissue is going to be much more effective, so I can get more oxygen into the bloodstream. All right. It could also be the case that there's a higher oxidative capacity in blood for somebody who's training, but that's not due to the arterial or venous difference in pressure of oxygen. That has to do potentially with the increased hemoglobin and the oxygen carrying molecules within the blood as well. So there are going to be other oxidative changes, other changes within the respiratory system that allow for more oxygen to be brought to the muscles. That's going to mean that more of these things called either hemoglobin, all right, hemoglobin, and also mitochondria. All right. So these are other adaptations that occur with the respiratory system. Let's go clear all drawings. Let's keep moving forward. So these are changes that are going to happen to the respiratory system. For an individual who is trained, their lungs are going to be able to give them the same amount of oxygen with less breaths per minute than somebody who is not trained. And they may also be able to change their breath to step ratio more effectively than somebody who is untrained as well. So these are all adaptations that happen to the lungs, but now there are adaptations that happen to the muscle. And some of those adaptations are based on the fiber type and the amount of blood vessels, but also based on the amount of the red blood cells that are attaching to oxygen. And in particular here, it's hemoglobin. All right, so there's going to be an increase in the amount of hemoglobin. Now, it's not going to increase necessarily hemoglobin. Man, this is jumpy today, hemoglobin. It's not necessarily going to increase the overall ability for hemoglobin to attach to oxygen. Remember, hemoglobin is a molecule that has 4 sites on it. And each of these sites is going to attach to an oxygen molecule. And that oxygen molecule is going to get brought to the muscle fibers so that the oxygen can be utilized to break down ATP. For the most part, you have like about 98% saturation rate, even at rest for untrained individuals on this hemoglobin. So it's not necessarily going to be the case that there's a better affinity or a better opportunity for oxygen to attach to hemoglobin. It's that the hemoglobin content is going to increase. So there's more hemoglobin in each amount or volume of blood, as opposed to it increasing its ability to attach to oxygen. So there's going to be increased hemoglobin. There's going to be increase in size and the number of type 1 muscle fibers. Type 1 is your slow twitch or endurance muscle fiber types. Now, it could be the case that some type 2 muscle fiber types switch because of hyperplasia to type 1 muscle fiber types or whatever. But again, there's not as much research to suggest that that happens. There is more research to suggest that type 2 or fast twitch muscle fiber types can perform a little bit more like type 1 muscle fiber types. They can transition to type 2A muscle fiber types to utilize oxygen more effectively. Capillary supply is going to increase. It's the number of these very teeniest veins at the very end of the vascular system. There's going to be an increase in capillaries that are providing the muscle fibers with oxygen. And remember, that's going to work in conjunction with the fact that the blood plasma volume is increasing. And if the blood plasma volume increases, it makes the blood less thick. And if the blood is less thick, then it's going to be able to get into the very teeniest of these little capillaries, which is going to be able to distribute more blood further down that vascularization chain. So adaptations that happen at the muscular level have to do with physical increases in fiber type, size, capillary density, and hemoglobin. But there are also other increases in enzymatic activity, specifically to things like succinate dehydrogenase or citrate synthase. And let's erase these, clear all drawings. And then there's also going to be an increase in mitochondria. So mitochondria is where the carbohydrate is broken down for ATP. So there's going to be a better opportunity to break down sugars. And then there's going to be other changes in oxidative enzymes. So one of the things that you would note is that there are increases in, say, for instance, VO2 max. All right, but those changes in VO2 max, and this is months of training, those changes in VO2 max seem to plateau at about 2 months of training. So if you're getting improvement in sport performance, because of resistance training, because of aerobic training, the adaptations to anaerobic training in regards to VO2 max and all of those lung related changes are going to top off, it seems, in about 2 months or so. Maybe, you know, it goes up, 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 and then it starts to plateau a little bit. Maybe you could say that those training effects kind of plateau at about 3 months. All right, so let's say 3 months instead of 2 months. All right, so 3 months instead of 2 months is where your VO2 max changes plateau. But if I take a look at the changes in my succinate dehydrogenase or other enzymatic activity that are associated with, with bringing oxygen and breaking down oxygen for fuel, if I look at some of those enzymes, you can see that with months of training, there is no plateau effect necessarily of succinate dehydrogenase activity increase until maybe 7 months of training. So although your VO2 max changes with resistance and endurance training kind of peter out and plateau out at about 2 to 3 months of training, there are other training adaptations that continue to increase. So it could be that the improvement in sport performance at month 3, 4, and 5 is due to increases in enzymatic activity, like succinate dehydrogenase, or if you look at the pattern of this particular enzyme as well, it's very similar. So VO2 max plateaus, increase in succinate dehydrogenase activity still increases, and there are increasing in training distance that kind of map over, or that are very similar to the increases in the changes in that enzymatic activity. So it could be that a lot of the changes and improvements to endurance training based on VO2 max, the improvements in training ability measured in training distance is not necessarily because I'm able to pull more oxygen in. It could be that there are enzymatic activities that are occurring that that allow for that improvement to continue, even though you're not necessarily getting gains in VO2 max any longer. All right, so, and these are untrained versus moderately trained versus highly trained athletes. Here, let's go like this. And it shows that succinate dehydrogenase and citrate synthase, which are two enzymes that are utilized to catalyze the Krebs cycle and the utilization of oxygen for fuel, you'll notice that with higher intensity training, there is an even greater increase in those activities. All right, so it could be the case that there are enzymatic activities that are at play that are leading to increases in sport performance above and beyond changes to VO2 max and heart rate associated with endurance training. With aerobic training, now these things here are all muscular associated changes, but there are other changes that are occurring not because of muscle, but because of your enzymatic activity. And now there are changes also because of metabolics. So it seems to be that the lactate threshold increases. So an individual who is exercising, their lactate threshold happens at a later bout of more intense exercise. So as their treadmill speed increases, they're able to do more intense exercise before they reach their blood lactate threshold, which means they're able to get more and more oxygen in, all right, which means that that's going to have an impact on their respiratory exchange ratio. You'll notice that for a trained athlete, their respiratory exchange ratio decreases compared to those individuals who are not trained. And what does a decrease in the respiratory exchange ratio with aerobic training indicate? What does that mean? Aubrey, what does it mean that if I'm training or I'm untrained, my respiratory exchange ratio is higher than an individual who is trained at a particular bout of activity? What does that mean?
I mean, so if your respiratory exchange ratio
Goes closer to 7. What does that mean?
that you're metabolizing fat.
Right. So that's a big modulation to the metabolic process of an individual who's training. Remember, carbohydrate and sugars are fuel that our body wants to hold on to. This is like the most pure version of gasoline for the brain and for the body. So the body wants to store this glucose for longer. And now as I get more trained, my body realizes more and more the importance of glucose. So as I train, my body changes its metabolic kind of process so that it starts to burn fat first and saves this glucose for later. So one of the adaptations to aerobic training, especially for individuals who are doing long bouts of endurance training, is that their body is going to start to burn fat before it's going to start to burn glucose. Save the sugars for later on, save the sugars for your central nervous system functioning, and burn fat stores beforehand. So that's going to be another major adaptation to aerobic training, is the utilization of fat stores as opposed to glucose stores. And that's going to make it so that it's easier to weight manage. So that's another metabolic change associated with aerobic training. Did anybody have any questions or anything? All right, so let's see. I think we're probably almost done. So resting in submaximal VO2 max, your resting VO2 max is not going to really be changed because you don't need more oxygen at rest. So resting VO2 max is not going to really have a big big impact. And also submaximal VO2 max is going to be relatively unchanged. But maximal VO2 max, max VO2 is going to increase. It's the best indicator that we have of cardiorespiratory fitness. That's why I want to give you guys a way to accurately estimate VO2 max. But in our lab, we only have very few resources. So to me, I think that if we use the Queen's College step test, there's very few things that we need. You need a metronome, number one. You need actually a step. And I'll show you how to do this, but we need a step so that we can go up and down the step. We need a metronome so that we can tell, and I guess we need a ruler. So I make sure that the step is the right height. We need a ruler. We're going to need a metronome. All right, a metronome. We're going to need somebody to count. Metronome. You're going to need somebody who can count your heart rate. So we're going to need either you can count your heart rate, or you can have an exercise specialist or one of your lab mates help you. You're going to need your heart rate, and then you're going to need some graphs. You're going to need to be able to take that heart rate here and plug it into either some graphs or some equations. All right, so if we have these tools here, a step, a ruler, a metronome, a heart rate, and graphs, then in 3 minutes, time, I can get you an assessment of VO2 max without any tools. And I think that's pretty powerful, because if I can estimate your VO2 max, that's the best indicator of cardiorespiratory fitness. So I would give you guys the ability to, or we should learn how to do heart rate. We should learn how to do blood pressure, which we've already done pretty well. I'm pretty sure that we're making progress with those. Then the next thing after that we have to do is your body comp, so your composition. But that's going to be easy, I think. What we should do is I should probably show you the procedure for doing skin calipers, but I think that you should go, and I was just walking Target yesterday near the bath department, and I saw that they had a scale that does body composition for $19.99. So I think that we can save a lot of time teaching you guys skin calipers. And I'll show you the other thing is so let me 1 second. I don't think I have this right here. I have a skin caliper in my bag that I use, but it's just like this piece of plastic crap that's not going to work great anyway. So even if we did skin caliper stuff, I just don't think it's going to be accurate. So why not just skip that and tell you guys, go get a scale so you can do body comp. But now we're going to be able to do VO2 max. So we've got our heart rate and blood pressure, you got your body comp stuff, and now we're going to give you an assessment of VO2 max. And all of a sudden, with very little resources at all, we almost have a complete assessment of cardiovascular fitness. And now what we need to do is, if I can tell you what my body composition is, then I can plug that into my resting metabolic rate, RMR, is equal to my 500 plus 22 times my fat-free mass, 500 plus 22 times my fat-free mass. And this equation here is great. And then if I know what my fat-free mass is, I know what my energy in and my energy out is. And then all of a sudden, with just some really simple tools, and then if I give you my exchange program and I give you that health-calc calculator so you can tell me what my energy out is, all of a sudden, with very minimal tools and maybe spending $19.99, I can get people a complete cardiac and cardiovascular fitness assessment. And that's what we're pretty much doing in our lab for this semester. All right, I want to be able to give you the biggest bang, and it's like the biggest bang for the buck. It's not even the biggest bang for the buck. It's like the biggest bang for no buck, right? Actually, the biggest bang for $19.99, and then you can get all this stuff for free. So that's kind of why I'm focusing on these assessments for our lab work, because I don't need too many resources, and there are valid assessments of the things that we're looking at. Anybody have any questions? Okay. Let's see where we're at. In terms of, let's just see. We only have a couple more slides left. Maybe what we'll do is we'll stop here for right now and we'll finish the rest of it. All right. I think that's probably pretty good. All right. Right now it's 10:04. It's pretty early. It's interesting. All right. I may as well. All right. I think that's probably good for right now. All right. I think that's almost the entire chapter. Maybe what we can do is, has anybody finished that heart rate and blood pressure lab at all? Has anybody taken a look at that? Yes, Sydney, did you complete it?
Yeah, the lab, but I haven't finished the lab report yet.
And I understand that. How many heartbeats could you save over the course of a lifetime if you reduced your heart rate by 4 beats a minute? I think that's what the lab asks. How many heartbeats over the course of your lifetime do you think you could save?
I think it says 20 beats per minute.
So you reduce it from 80 beats per minute to 60 beats per minute, right? Let's say.
Sorry. And it says beats saved over a lifetime is 516,840,000.
Yeah, I mean, and now all of a sudden that has a huge impact on cardiovascular health and overall cardiovascular fitness, right? If you can do a little bit of endurance training and you can reduce your resting heart rate by 20 beats per minute. Now that's, if you reduce it by 20 beats per minute, you save yourself 55, I think you said 555 million. Is that correct? Right. So, I mean, if I reduce that by 10 beats per minute, I'm going to reduce my heart beating 200 million times. And if I can just reduce it by 5 beats per minute, I'm going to reduce it by 100 million beats per my lifetime, which I'm sure is probably going to help impact my cardiovascular health for sure. Okay. Does anybody have any questions